Have you ever pondered the universe? Have you ever wondered about those bright, fleeting lights that grace our night sky? Today, we delve into the world of supernovae. Supernovae, the brilliant, ephemeral explosions that punctuate the celestial canvas, are considered one of the most energetic and luminous events in the observable universe. These cosmic pyrotechnics are not merely dazzling light shows. They are, in fact, the final act in the life of certain stars, a grand finale that outshines entire galaxies and radiates more energy in a single moment than our sun will in its entire lifetime. These celestial fireworks are more than just awe-inspiring spectacles. They are cosmic creators, cosmic destroyers, and cosmic illuminators. They are the forges where elements heavier than iron are birthed, the sculptors of interstellar medium, and the lighthouses that guide our understanding of the cosmos. So, ready yourself for an astronomical adventure. Join us as we embark on a journey to understand these celestial explosions. So what exactly is a supernova? And how many types are there? Well, a supernova is an astronomical event that occurs when a star exhausts its nuclear fuel and undergoes a violent explosion, outshining entire galaxies and radiating more energy than our sun will in its entire lifetime. Now, let's talk types, because not all supernovae are created equal. There are several main types, each with unique mechanisms and progenitor stars. First up, we have Type 1a supernovae. These are binary systems where one star is a white dwarf. The dwarf star feeds off its partner, accumulating matter until it reaches a critical mass and explodes in a thermonuclear blast. Fascinating, isn't it? Then come Type 1b and 1c supernovae. These are the result of massive stars shedding their outer hydrogen layers before their core collapses. The key difference between 1b and 1c lies in the presence of helium. Type 1b supernovae show strong helium lines in their spectra, while Type 1c do not. Next up, we have Type 2 supernovae, further divided into Type 2L and 2P. These are the end product of supergiant stars with masses several times that of our sun. In these stars, the core runs out of nuclear fuel and collapses under its own gravity, triggering a catastrophic explosion. Type 2L supernovae display a linear decline in their light curves, while 2P exhibit a plateau phase. Each type of supernova paints a unique picture of the life and death of stars. They are the celestial artists, sketching out the story of stellar evolution in the cosmos. From white dwarfs in binary systems reaching a critical mass to the catastrophic collapse of a supergiant's core, each supernova tells us a tale of cosmic proportions. It's as if the universe itself is narrating to us the dramatic stories of its stellar inhabitants. So the next time you look up at the stars, remember that each one is living out its own unique life, and who knows, maybe one day it will end in a spectacular supernova, leaving a lasting impression on the canvas of the cosmos. Each type of supernova, unique in its own way, paints a picture of the life and death of stars. Let's delve into the life cycle of massive stars leading to supernovae. Picture a star, not unlike our own sun, but far more massive. These celestial giants have a life cycle that's both fascinating and complex, and it all begins with a cloud of dust and gas in space. As gravity pulls this material together, a protostar forms, and as the pressure and temperature rise, nuclear fusion begins, marking the birth of a star. During the majority of a star's life, known as the main sequence, it burns hydrogen in its core, converting it into helium through a process called fusion. This process releases a tremendous amount of energy, which we see as light and heat. The pressure from this energy counteracts the force of gravity, maintaining the star's stable size. However, as stars exhaust their hydrogen supply, they begin to fuse helium into heavier elements like carbon and oxygen. This process continues, creating layers of increasingly heavy elements within the star's core. It's a bit like the layers of an onion, each one representing a different stage in the star's life. Eventually, the star begins to fuse lighter elements into iron. Here's where things take a turn. Iron fusion doesn't generate energy, it absorbs it. This creates an energy deficit, causing the core to collapse under its own gravity. The outer layers of the star, having nothing left to hold them up, follow suit, crashing inward at a significant fraction of the speed of light. This violent collapse triggers a shock wave that blasts the outer layers of the star into space in a cataclysmic explosion we know as a supernova. The core that remains can turn into a neutron star, or, if massive enough, a black hole. The life of a star, full of twists and turns, ultimately leads to a spectacular finale, a supernova. This dramatic ending, however, is just the beginning of a new cycle in the cosmos. It's a cycle of death and rebirth, of chaos and creation, that has been unfolding for billions of years, shaping the universe as we know it today. Now that we understand what a supernova is, let's explore their characteristics. A supernova isn't just a one-off explosion, it's a stellar performance that unfolds over time. This display of cosmic fireworks is charted using what we call a light curve. This curve tracks the brightness of the supernova over time, starting from the initial explosion, reaching a peak and then gradually fading away. But it's not just about the spectacle. The light curve gives us key insights into the physics of the explosion, the energy of the blast, and the elements that are being formed. Each type of supernova has a distinctive light curve. Type 1, a supernova, for instance, have a quick rise to maximum brightness, followed by a slower, more gradual decline. On the other hand, Type 2 supernovae show a more complex light curve, often with a plateau phase before a steady decline. These differences are not random, but reflect the underlying mechanisms of the explosion and the structure of the progenitor star. Now let's turn our attention to the spectral signatures of supernovae. Just as our fingerprints are unique to us, the spectrum of a supernova is unique to its type and stage of evolution. It's like a barcode, revealing the composition of the material being ejected in the explosion. The spectrum shows us emission lines which correspond to different elements. For example, the presence of silicon in the early stages of a Type 1a supernova or hydrogen lines in a Type 2 supernova tells us a lot about what's going on inside the explosion. But what happens when the show is over? What's left behind after the curtain falls on a supernova? The remnants of these cosmic cataclysms are as varied as the stars themselves. If the original star was less than about 20 times the mass of our Sun, it collapses under its own gravity to form an extremely dense neutron star, cramming more mass than our Sun into a sphere only about 20 kilometers across. For more massive stars, even this extreme compression isn't enough to halt the collapse. The core implodes to a point of infinite density, creating a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. And then there's the supernova remnant, the outer layers of the star that were blasted into space by the explosion. These remnants expand outward, creating beautifully intricate structures of glowing gas and dust. Over time, they mix with the surrounding interstellar medium, seeding it with heavy elements and triggering the birth of new stars. From their light curves to remnants, supernovae are as complex as they are fascinating. Beyond their celestial beauty, supernovae play a pivotal role in the universe. Let's explore their impact. First, let's dive into nucleosynthesis. Supernovae are the universe's alchemists, creating and dispersing elements heavier than helium. When a star goes supernova, it doesn't just explode, it's a chemical factory in overdrive. The intense heat and pressure trigger nuclear reactions, forging elements like gold, platinum, and uranium. These elements, essential for life and planetary formation, are then blasted into space, spreading the seeds of future worlds. Next, we turn to star formation. The shock waves from supernovae can compress the interstellar medium, this vast, cold space between stars. This compression can trigger the collapse of a gas cloud, sparking the birth of new stars. So in a way, the death of one star can lead to the birth of others. It's a cosmic cycle of life and death, played out on an astronomical scale. Now let's talk about galactic evolution. Supernovae are key players in the shaping and evolution of galaxies. When a supernova explodes, it disperses heavy elements throughout the galaxy. This process, known as chemical enrichment, plays a major role in determining the galaxy's structure and evolution. Over billions of years, supernovae have helped to sculpt the galaxies we see today, from spirals like our own Milky Way to the vast elliptical galaxies. Finally, we come to cosmology, the study of the universe's origin, evolution, and eventual fate. Here, supernovae Specifically, Type 1a supernovae play a crucial role. Because these supernovae have a consistent peak brightness, they serve as cosmic yardsticks, helping astronomers measure the universe's expansion rate. Observations of distant supernovae have been instrumental in discovering the mysterious force we now call dark energy, which is causing the universe's expansion to accelerate. Supernovae are not just stellar spectacles. They're crucial to the life cycle of the universe, from the formation of new stars and galaxies to the synthesis of heavy elements. They've even helped us unravel some of the universe's deepest mysteries, like the nature of dark energy. In the grand tapestry of the cosmos, supernovae are the threads of change. They bring death, yes, but also life. They forge elements and shape galaxies. They illuminate the distant past and hint at the universe's future. They are, in essence, the universe's architects, builders, and artists, continually reshaping and redefining the cosmic landscape. Supernovae, the cosmic alchemists, shape the universe in ways more profound than their fleeting yet mesmerizing light shows. As we stand on the precipice of understanding, let's delve deeper into the mysteries of supernovae. Our knowledge of these stellar explosions has been shaped by centuries of observation and research. Historical observations of supernovae, such as the Crab Nebula event in the year 1054 or the Tycho's star of 1572, have provided invaluable insights into these cosmic phenomena. These celestial fireworks, documented by astronomers of yore, have paved the way for our current understanding of stellar evolution and death. Fast forward to the present day, our exploration of supernovae is becoming increasingly sophisticated. Modern telescopes, both ground-based and spaceborne, are capturing data across multiple wavelengths, from radio to gamma rays. This multi-messenger astronomy approach is revealing new facets of supernovae, including the intricate dance of magnetic fields and fluid dynamics, the role of neutrinos, and the processes that govern the transport of energy through the supernova ejecta. But as with any scientific endeavor, each answer only leads to more questions. There are still many unsolved mysteries in supernova research. For instance, what exactly triggers the final core collapse in massive stars? How do progenitor stars or parent stars influence the type and outcomes of supernovae? And perhaps most intriguingly, how do supernovae contribute to the mysterious dark energy, that elusive force accelerating the expansion of the universe? These questions, and many others, continue to fuel ongoing research efforts. From theoretical models that simulate supernova explosions in supercomputers, to new observation techniques that capture fleeting neutrinos or gravitational waves, the hunt for answers is as intense as ever. The enigma of supernovae continues to challenge and inspire us, pushing the boundaries of our understanding. As we delve deeper into their mysteries, we are not only unraveling the life story of stars, but also piecing together the cosmic tapestry of our universe. And who knows? The answers we seek might just reshape our understanding of the cosmos. Our journey into the world of supernovae has been enlightening, to say the least. We've navigated the intricate life cycles of massive stars, witnessing the buildup of iron in their cores and the cataclysmic explosions that follow. We've dissected the mechanisms behind these stellar fireworks, from core collapse to thermonuclear runaway, and have become familiar with the luminous signatures they leave behind. We've also explored the cosmic aftermath of these events, from the birth of neutron stars and black holes to the chemical factories churning out the elements essential for life. We've seen how supernovae contribute to the evolution of galaxies, and how they've helped us measure the expansion rate of the universe. We've even delved into the ongoing research and the tantalizing mysteries that keep astronomers awake at night. As we gaze at the stars, let's remember the power and beauty of supernovae, a testament to the dynamism of our universe. Until next time, keep exploring.